The grand question, where did it all begin? This question has fascinated humanity for millennia, sparking curiosity and wonder. When we look up at the night sky, it's like peering into a canvas of endless wonder. Each star, a distant sun, each galaxy, a collection of countless stars. It's filled with twinkling stars and distant, swirling galaxies. The vastness of space is both humbling and awe-inspiring. For thousands of years, we've gazed at this cosmic spectacle and asked a simple question: where did all of this come from? Ancient civilizations built observatories and created myths to explain the heavens. How did our universe start? What was the catalyst for the birth of everything we see around us? The universe is unimaginably vast. Its scale is beyond our everyday comprehension. Our Earth is just one small planet, orbiting a rather ordinary star. Yet this star is just one of billions in our Milky Way galaxy. Our star is one of billions in our Milky Way galaxy, a galaxy that itself is just one of countless others. And there are billions of galaxies, each a magnificent island of stars scattered through the cosmic ocean. The sheer number of stars and galaxies is mind-boggling. The sheer scale is truly breathtaking, making us feel small yet curious. It ignites a desire to understand our place in this vast expanse. So, how do we even start to answer these questions? How do we begin to unravel the mysteries of the universe? How do we probe such a deep past? The answers lie in the stars and the light they emit. We use the tools of science, observation, mathematics, and theory. These tools are our guides in this cosmic journey. These tools allow us to look back, to piece together the universe's history. They help us understand the events that shaped the cosmos. The best answer we have today? It comes from a groundbreaking theory. It's called the Big Bang Theory. This theory describes a universe born from a singular explosive event. It describes a universe born from fire, expanding and cooling over billions of years to become the cosmos we see now. This theory continues to evolve as we learn more. When many people hear Big Bang, they imagine a giant explosion, like a bomb going off in space. But this picture is not quite right. It's a common misunderstanding. The name can be a little misleading. It wasn't an explosion in space because space itself did not exist yet, at least not as we know it. We need to think differently about this event. The Big Bang was an expansion of space itself. Imagine a tiny, compressed point containing all energy, all matter. Then, space itself began to stretch. It started to grow rapidly, carrying everything along with it, like yeast making bread rise. Everything we see around us, every star, every galaxy, every atom, was once packed together in an incredibly hot, dense state. Space and time themselves began then. The universe is the expanding space, and its story started 13.8 billion years ago. So, what was there before the expansion? Science points to a singularity. This is a challenging idea. It's a point of infinite density and infinite temperature. Imagine all the stuff of the universe, all the energy, all the matter, squeezed into a space smaller than an atom. Infinitely smaller, in fact. A point of zero volume. This singularity is a theoretical concept. It comes from our equations, Albert Einstein's theory of general relativity. It predicts such a point when we run time backwards, back towards the very beginning. Our current laws of physics, they break down at a singularity. They cannot describe what happens there. It is the edge of our understanding. Space and time as we know them began with the Big Bang. From this incredibly dense state, the universe began its vast expansion, and that expansion continues today. Immediately after this initial moment, the universe began to expand, and it expanded incredibly fast. This rapid expansion is known as cosmic inflation, a brief but monumental period that set the stage for everything we observe today. This was not matter flying through space, it was space itself stretching. Imagine the very fabric of the cosmos being pulled in all directions, creating more space between objects. Think of the fabric of reality being pulled in all directions. This expansion was fundamental. It wasn't just a simple movement, it was a transformation of the universe's very structure. It shaped everything that followed. The galaxies, stars, and planets we see today owe their existence to this initial expansion. It is the core of the Big Bang model. This model explains how the universe evolved from a hot, dense state to the vast cosmos we observe now. Imagine dots painted on a balloon. As you inflate the balloon, the rubber surface stretches and the dots move further apart. As you inflate the balloon, the rubber surface stretches and the dots move further apart. This is a simple analogy to help visualize the concept, not because they are moving on the surface, but because the surface itself is growing. The space between the dots increases as the balloon expands. Galaxies are like those dots. They are carried along by expanding space. They are carried along by expanding space. The further away a galaxy is, the faster it appears to move from us. The further away a galaxy is, the faster it appears to move from us. This expansion caused cooling. The early universe was intensely hot. The early universe was intensely hot. As space expanded, energy spread out. As space expanded, energy spread out. It became less concentrated, so the overall temperature dropped. This cooling was crucial. It became less concentrated, so the overall temperature dropped. This cooling was crucial. It allowed particles to form, then atoms like hydrogen and helium. It allowed particles to form, then atoms like hydrogen and helium. These atoms eventually came together to form stars and galaxies. And this expansion is still happening. The universe continues to stretch, carrying galaxies further apart, shaping the cosmos as we know it. Section 5. A Whisper from the Dawn, the Cosmic Microwave Background. As the young universe expanded, it also cooled down. For the first few 100,000 years it was a superheated fog, a plasma of charged particles. Protons and electrons whizzed around and light or photons could not travel far. They kept bumping into these particles. The universe was opaque, like trying to see through a dense cloud. Then, a critical moment arrived. About 380,000 years after the Big Bang, the universe cooled enough to a few thousand degrees Celsius. At this temperature, electrons and protons could combine to form neutral atoms, mostly hydrogen and helium. Suddenly the fog cleared. Photons were free to travel and light could finally stream across space. This first light is still traveling. It fills the entire universe. It is called the Cosmic Microwave Background, or CMB for short. Section 6. Tuning in. The discovery of the CMB. The existence of this ancient light, the cosmic microwave background, was actually predicted by scientists years before it was found. This faint glow, a remnant from the early universe, was theorized to be a crucial piece of evidence for the Big Bang theory. Physicists like George Gamow and his colleagues Ralph Alpher and Robert Herman calculated that if the Big Bang happened, there should be a relic radiation, a faint glow left over with a temperature of a few Kelvin. Their calculations were groundbreaking, setting the stage for future discoveries. Then, in 1964, came a surprise. A discovery that would change our understanding of the universe. Two American radio astronomers, Arno Penzias and Robert Wilson, were working at Bell Labs in New Jersey. They were not looking for the CMB, they were simply trying to detect radio waves from space. They were using a large horn antenna, trying to detect radio waves from space. This antenna was state-of-the-art for its time, designed to pick up the faintest signals from the cosmos. They found a persistent, faint noise, a hiss, coming from all directions. This noise was unlike anything they had encountered before. It was there day and night, no matter where they pointed the antenna. The signal was omnipresent, a constant hum in their data. They tried everything to remove it. They checked their equipment meticulously, ensuring there were no faults. They even cleaned pigeon droppings from the antenna, thinking it might be the cause. But the noise remained. The persistent hiss was still there, baffling them. It was a cosmic signal. A signal that was not from their equipment but from the universe itself. They didn't know what it was at first. The origin of this noise was a mystery that needed solving. It turned out they had stumbled upon the cosmic microwave background, the very afterglow predicted by Gamow. This discovery was monumental, providing the evidence needed to support the Big Bang theory. Section 7. Architects of Understanding, Key Scientists. The Big Bang theory wasn't one person's idea. It grew from many brilliant minds over many decades of research. One of the earliest pioneers was a Belgian priest and physicist named Georges Lemaitre. In the 1920s, he proposed that the universe was expanding. He imagined a primeval atom, a cosmic egg from which everything began. Then there was Edwin Hubble, an American astronomer. In 1929, he made a crucial observation. Using the powerful Mount Wilson telescope, he saw that distant galaxies are all moving away from us, and the further away they are, the faster they are receding. This is Hubble's law. It was strong proof of an expanding universe. Even before Hubble's observations, Russian mathematician Alexander Friedmann had found solutions to Einstein's equations. These solutions described a dynamic universe, one that could expand or contract. This was a departure from Einstein's own initial belief in a static universe. Section 8. More than a hunch. Evidence for the Big Bang. The Big Bang is not just a guess. It is not a wild story. It is a robust scientific theory. This means it is supported by evidence. Lots of different observations all point to the same conclusion. The universe began in a hot, dense state and has been expanding ever since. This consistency is very powerful. It gives us confidence in the model. The cosmic microwave background is key. We have already discussed its discovery. Its near-perfect uniformity with tiny temperature fluctuations precisely matches predictions. These fluctuations were the seeds for future galaxy formation. No other theory explains the CMB so well. It is a direct window to the early universe, a baby picture of the cosmos. Another strong piece of evidence is the abundance of light elements. Section 9. Our Cosmic Story, the Legacy of the Big Bang. The Big Bang Theory tells us something profound about our place in the universe. We are not separate from the cosmos. We are a product of its evolution. The atoms in our bodies, the carbon, the oxygen, the iron, were forged in stars. Stars that form from the primordial gas left over from the Big Bang. We are, quite literally, stardust. Understanding the Big Bang gives us a sense of our origins. It tells us the universe had a beginning. It has not existed forever. It has a history, a story, and we are part of that ongoing story. This is a powerful shift in perspective, from an eternal, unchanging cosmos to a dynamic, evolving one. It opens up new ways of thinking. Of course, the theory is not complete. It raises new questions.